In this lesson, we're going to continue working with equivalent expressions, and what we're doing today is we're going to take some what look like kind of complicated expressions, and I'm going to show you a way to make them less complicated by what we call combining like terms. Before we do that, though, I want to finish up what we did yesterday with the commutative and the associative properties. So it's going to be a little bit of a repeat of what the video was yesterday. You can fast forward that if you already looked at that part, and we'll get to the new stuff. But for now, let's go over the do now answers and over the homework. So go ahead and turn to the next page. So the first question asks if there is a commutative property of division. So I took a division problem, 20 divided by 4, and then changed the positions, because that's what we do with the commutative property, to 4 over 20. However, 20 divided by 4 is 5. 4 over 20 is equal to 1/5, or 0.2, so you can't change positions in division and get equivalent expressions. So the answer is no, there is no commutative property of division. For number 2, this is an introduction to what we're doing today. I want you to think about how you added what's in these two boxes. And I just want you to think about that. You didn't add everything here to everything here. You can only add the apples to the apples, and you can only add the books to the books. So there's not 12 of stuff. There's still just 5 apples and 7 books. We can only add the items that are the same, okay? And that's going to be a big part of what we do today. So you could have had a couple of things here. I had 5 apples and 7 books. You could have an actual expression, something like 5a plus 7b, okay? Or you could draw 5 apples and draw 7 books. All right, let's take a quick look at the homework answers. Here are the answers again. The point of this is just to make sure you can distinguish between the associative property and the commutative property. Remember, commutative is about moving things around. Associative is about associating different groups together using parentheses. All right, so let's review those again real quickly. So turn to the next page, please. So these properties, again, only work with addition and multiplication. They do not work with division. They do not work with subtraction. So real quickly, commutative property of addition just means that I can have 2 plus 3, and that's a terrible 3. And that's the same as 3 plus 2. And I can have variables in there as well. I could have 2 plus n, and that's the same thing as n plus 2. Remember, commutative is I'm moving things around, so I'm changing the position of the 2 and the n and the n and the 2. Multiplication is the same. I can do 2 times 3, and that's the same as 3 times 2. And I can also do it with variables. I can have 2n, and that's the same as n2. Same deal. All right, so let's take a look at this first example. And it's asking if n plus 9 plus 2 is the same as 9 plus 2 plus n. And the way I want you to figure that out is pick a value for n and see if they are the same. And I'm going to do that for you real quickly right now. So I'm going to say n equal to 1. I'm going to keep it simple. So if I substitute that back in, I'm going to have 1 plus 9 plus 2. And I'm wondering if that's equal to 9 plus 2 plus 1. And of course they are. 1 plus 9 is 10, plus 2 is 12, 9 plus 2 is 11, plus 1 is 12. They are the same. So that just kind of shows you how it works. Now, associative property is how we group things differently. So for addition, I might have something like 2 plus 3 plus 4, but that's going to be the same as 2 plus 3 plus 4, where I just have them grouped differently by the parentheses. Associative property is all about the parentheses. And again, I can also do this with variables. N plus 3 plus 4 is the same as n plus 3 plus 4. And the same thing goes with the associative property of multiplication. I can have 2 times 3 times 4, and that's the same as 4 times 2 times 3. Oops. That's the commutative property. Never mind. Let's start that again. All right. So I could have 2 times 3 times 4, but that's the same as 2 times 3 times 4. Okay? And again, I can have a variable sitting in here as well. Let's say 2 times n times 4, and that's the same as 2n times 4. Again, just grouping it differently. So this is the same deal. Imagine if 2 is equal to, I don't know, let's say 4. So I'm going to see if these two expressions here are the same when 2 is equal to 4. And we're going to get 2 times 4 times 2. And we're going to have also 3 times 4 times 2. That'll be the same thing. We do parentheses first. So we have to get the 8 there. And then 3 times 8 is 24. Here we do the parentheses first. We get 12. So 12 times 2. There's also 24. So you can see that again. Okay, go ahead and turn to the next page, and we're going to practice this a little bit. I want you to pause the video and determine if these expressions are equivalent, and I want you to use a specific value of m, any value that you want, to make that point. So go ahead and pause the video, work on these problems, then come back and check your answers. All right, check out these answers. For number 1, I let m equal to 3, and when I substituted 3 for m, I have 3 times 5. On the right-hand side, I have 5 times 3. They're both equal to 15. So you can see that the commutative property works here. Here we're looking at an associative property problem. I let r equal 1, so I substitute 1 in for r in both the left and the right-hand side. When I do the parentheses, 1 plus 1/2 is 1.5. Add that to 8, I get 9.5. On the right-hand side, I add the 8 plus the 1 first, I get 9, plus the 1/2 is 9.5. So once again, you can see that the associative property, when you're using addition, works. However, I have subtraction here. So I let n equal to 2. I did 5 minus 2, and I got 3. But when I do 2 minus 5 and change the position, I get negative 3. So they are not equivalent, so we've already talked about this. It does not hold for subtraction. All right, go ahead and turn to the next page. So now we're going to get into the new stuff, but there are a little bit of notes that I need you to take. So let's start. A term, we've talked about this before, a term is part of an expression. And like terms are terms that have the same variable raised to the same power. And we're talking about exponents here, okay? expressions can be simplified by combining like terms. In the simplified, both the original expression and the simplified expression are equivalent. Okay, I'm going to stop to let the siren go past. All right, so a couple things I want to point out to you before we start to do an example is whenever we have a letter by itself, the coefficient is 1. That's really important. And whenever we don't have an exponent that we see, that exponent is like 1. So that's also helpful to know as well. So we're going to do an example. I'm going to show you a couple of different techniques that are very similar but not quite the same in order to do these. All right, so we have this expression. We have lots of terms, and we want to identify the like terms first. So I'm going to use what I call the shape technique to start out with this. And so I have a 3x. I'm going to put a circle under that. Now I need to find every other term that is just an x and no exponent. So that's a constant that has a 2 as an exponent. That's a constant, has a 2 as an exponent. Here's another x with no exponent, so I'm going to put an O under that, or a circle. And then, of course, we have another constant. All right. Now, here's a constant. This has an exponent, so it's not the same. Then here's another constant. So I'm going to put boxes under that. That's a terrible box, but I think you get the idea. And then we have a 2x squared. We have no other term that has an exponent of 2. So I'm just going to put a triangle under that just to separate it from the others. Now we're going to combine the terms that have the same shapes. And we're going to do that by adding the coefficients. So I have a 3x with a circle and a 5x with a circle. I'm going to combine them by adding the coefficients and keeping the variable. So that's going to give me 8x. Right, I'm getting that from here and here. I have 2 pieces that have squares or rectangles below them. Those are our 2 constants. So we're going to add those together. So that's going to give me 7 and 4. That's going to give me 11, right? And that comes from here and here. And then we only have the triangle left, and there's nothing to combine it with, so it just comes straight down as it is. And that's going to be 2x squared. So these expressions are equivalent. One is just a simplified version of this one. And we got it down, instead of 1, 2, 3, 4, 5 terms, we have it down to 3 terms. And that's going to be very helpful to you when we start to actually solve equations. All right, I want to show you this example again with a different technique, then I'm going to let you do some practice. So go ahead and turn to the next page. So here's the same problem, but we're going to use what I call the underline technique. So once again, I'm going to start with a 3x. I'm going to underline it with the exponent that's associated with it. So because this has no exponent, that means it's an exponent of 1. So I'm going to underline it once. I'm going to look for any other piece that has an exponent of 1. That doesn't, that doesn't, that does, so I'm going to also underline that once. This piece has an exponent of 2, so I'm going to underline that twice. And then generally I circle my constants. So now I just combine those pieces that are matching with the underlines or the circles. And so I'm going to combine my single underlines to get the 8x. my double underline to get the 2x squared, and my circled constants to get 11, which is just what we got on the page before. We get a different order, but remember, commutative property means we can put them in any order that we want. All right, so I want you to pause the video and try these two problems. Use any technique that you want. This one is about perimeter, which means you are adding all the sides, so you might want to write that out before you start simplifying it. And go ahead and work on those, and you can come back and check to see how you did. All right, go ahead and check these answers out. The one thing that's a little bit different in this problem is we have a subtraction, and that's important. You can't ignore that. So we have like terms of k, but I have 4k minus, remember that's a 1k when we don't have a number there. That's why I get 3k here. In this one, again, I'm adding all of the sides together for perimeter. I have 3 pieces that have an x involved in it. So that's 2 plus 5 plus 4 to give me 11x. And I have a 4 and the 1 to give me the 5. All right, go ahead and turn to the next page for some more practice. Go ahead and pause the video and work on these problems, and then come back and check your answers. All right, check out these answers. Threw some fractions into this problem here. So just to confirm, we have 1/4 plus 3/4. That's going to give me a total of 4/4, which is the same as 1. And I don't normally write the 1 in front of it, but I could, right? That's the same as 1x squared. And then we have 3½ So 3 plus 1/2, I just did 3½. You could write that in proper as well, make it 7/2. Another perimeter problem. Remember, the perimeter is the length around, so you have to add all of the sides. That's what I'm doing here. Adding the like terms of 2x and 2x and 2x and 2x to get 8x, and then 1 plus 1 plus 1 plus 1 gives me 4. Then on this last one, I had a few x squared like terms that combined for 10. Also a few x terms that also combined for 10, and then my constant was 10. All right, so we'll have a little did you meet the target worksheet at the end. If there's time now between now and then, you can work on your homework and let me know if you have any questions.